Hey, let's look at the voltage division. So we have n elements. We assume the voltage here, the total voltage V, and the n impedances are given. And we're trying to find the voltage V sub k across the kth element. And in this case, we have we can write the element constant. So the element constant and that's V sub k equal Z sub k times I sub k. And based on the KCL, which is the connection constant, we have I sub k is equal I. Based on the equivalent impedance, we have V is equal I times Z sub EQ, or I is equal V over ZEQ. So if we substitute, let's see, this 2, this is the 1, this is 3, and we substitute 2 and 3 into 1, what do we get? We get V sub k is equal to Z sub k times V over ZEQ, right? So we can rewrite this slightly different as Z sub k over Z1 plus Z2 plus delta plus Zn. That's ZQ, Z sub EQ on the denominator times V, right? So this is the voltage division. So if you try to find the voltage across kth element, you just use that impedance divided by the whole thing, by the total impedance or the equivalent impedance. So this is the voltage division. But there's a catch here, and pay attention to we labeled all the elements across the all the voltage across the elements here are in the different direction. So let's see, if we choose a clockwise direction, and the total voltage V here is, this is the voltage rise from negative to positive, the voltage rise is V, and from positive to negative, the voltage drop across Z sub k is V sub k. So one is the rise, one is the drop. In that case, this equation is derived based on this convention, right? So if someone try to trick you and label the voltage V sub k the other way around. So let's see, if flip the plus minus sign, in that case you would have a negative sign. In that case, if you choose the clockwise direction or counterclockwise direction, both voltage, both V and V sub k would be voltage rises or voltage drops. So just pay attention to that. Let's look at an example. This example is in the Google Colab notes. Okay. So in this case, we have RLC in series, and we have voltage, sinusoidal voltage. Pay attention to the sinusoidal voltage here is given in sine, not cosine. And we're trying to find the equivalent impedance Z sub EQ seen by this source. And also we're trying to find the steady state voltage V sub R, and this voltage, and this voltage, and pay attention to the voltage reference mark for V sub L and V sub C, right? So the solution here is we want first convert the circuit into phasor. The solution, and so we transform the voltage source in sinusoidal into phasor, and also we need to find the impedances, right? So first, V sub S is based on these. The V sub S should be equal 10. The phase angle should be 30 minus 90, should be negative 60, because the V sub S T is equal 10 times cosine x 5000 t plus 30 minus 90 degrees, right? So therefore, that's equal 10 times the cosine 5000 t minus 60 degrees. And here we use the trig identity sine x is equal cosine x minus 90 degrees. Right. So the v sub s, we find that already, and we can find z sub r. Z sub r is just equal r, right? Z sub l it should be equal j omega l, and z sub c is equal 1 over j omega c. With all these in numbers, so we have r, l, and c's, you can find this all in numbers. So therefore, the ZEQ seen by the source would be equal ZR plus Z sub L plus Z sub C. So there is a number calculated in the Google Colab notes. Okay. So then the second one here is we're trying to find the voltages. And we first find the phasors. So in this case, the Z sub R and V sub R, we use voltage division. V sub R should be equal to Z sub R divided by ZEQ. And ZEQ now you already find this, this is known now since you had the solution there, and times V sub S. So everything is known. So you should be able to get a number here. And once you get that number, and the V sub RT should be just equal the magnitude of V sub R and times the phase angle times the cosine omega t, that's 5000 t, plus the angle of the V sub R. Right. So this should be, if you have the polar form, and you can convert that to the sinusoidal signal very quickly. And let's look at the V sub L. So V sub L in phasor, that should be equal Z sub L as ZEQ times Vs. Is that correct? Not really, because if you choose the clockwise direction, V sub S is the voltage rise, and V sub L also voltage rise. Then you should have a negative sign here, right? So in this case, you can also find the numbers. Everything is known. Everything is known here. So therefore, V sub L t is just equal the magnitude of V sub L times the cosine 5000 t. You substitute all the numbers. We have all the number calculated in the Google Colab notes. The reason I didn't bring it up because if I bring it up, my tablet is gonna get freeze up. I don't know why. And you can do the similar to find Z sub C, V sub C, right? So you can find V sub C, and then you can find VCT. So this is the solution we would have using the phasors. So we do not need the differential equation anymore, right? So that's the nice part. So this is a quick example show how we can use the voltage division to solve the problems. I will see you in next clip, which is the parallel conduction.